All right, so we'll see how this one works on this. So many ways to take a look at problems that are in dealing with growth and decay. So I actually would almost rather do 12 first because it's a little bit more straightforward, but I guess we'll take a look at number 11. So the half-life of chromium 51 is 27.7 days. So when I look at those things, what I know is in a physics class, they would like you to say it's something like this right here, that the amount that you would have is whatever your initial condition is 1/2 to the t over 27.7. Whereas in a calculus class, we like to do this kind of a deal right here. Well, it turns out there's a fairly straightforward thing we could do, because clearly if we divide both sides by whatever that initial condition, which is our constant, that just goes away, no big deal. And if I took the log of both sides, we know that that is going to pop in front. And over here, if I take the log of this, you get kt. Well, something really, really nice happens. Notice this side has a t in it, so does this. So if I divided both sides by that time, it's gone, and I have 1 over 27.7 natural logs of 1/2 is equal to k. And that is my growth rate. So I'm going to go ahead and grab that thing right here. So 1 divided by 27.7 times the natural log of 1/2, we're looking at negative 0.025. So my growth rate for this problem for part A is k, is approximately negative 0.025. And keep in mind, although that is a decimal and it's big and ugly, I'm going to store that as alpha. Let's go alpha k just so I can be consistent, because I will be using that throughout this problem. So what it asked me for is what is that initial condition? So there's a wide variety of ways that we could do this problem, but I think a nice creative way to do this problem is to start with the idea of, let's just pretend that we actually had 7.9. It says that was 6 days into the experiment. So I'm going to start at 6.9 e to the negative 0.25 t. And let's just say that that's my pretend equation. That's not the real equation. That kind of set times 0 is 6 days. That's a little bit weird. So what I decided to do is I'm just going to stick with that number, and I'm going to take 7.9 and I'm going to multiply it by e raised to the negative, actually k was already negative, wasn't it? Alpha k. And I'm going to use 6 days backwards in time. So I'm going to do k, that doesn't look like a k to me, k times negative 6. And if I did that, this would make times 0 6 days back. So effectively, I could reset the problem to being 9.179 e to the negative 0.025 t. This is the real equation by just going 6 days backwards in time. Now, for part C, it says, what is going to happen in 10 days? So all I have to do is find a of 10. Now, again, the power of storing these values in as you go is really, really quite substantial. And I just said that and I just messed that up. So let's store this as alpha A. So I have that. So I've got A times E raised to the K. Let's see, alpha K times 10 days. And so it appears to me that in 10 days, we should have 7.1475 grams. And then the last question that they asked, D, is when would it equal 1? So again, remember we have all this stuff in here that is stored. So if we were to divide both sides by this value, 1 over 9.197 equals e to this ugly power. We're going to take the log of both sides. Now keep in mind, although I'm writing these decimals down, I actually have the actual values sitting in my machine. So I'm going to take the natural log. Remember, I stored this one as the natural log was 1 over a, because I stored that one as a. And then I'm going to divide by this negative 0.025, which I stored as k. And it looks to me like my time would be approximately 88.597 days. So that's the end of problem 11. And I'm going to try to get to problem 12 because I have a meeting that starts in about 2 or 3 minutes. So I'll just be a moment late to that meeting, and that's okay. So a colony of widgets is growing at a rate proportional to the number of widgets. Now, by saying that, you're talking CE to the KT. That's automatically what that does. Technically, it says the rate of change of widgets, dWt equals kW. It automatically comes into that. So you have 1 over W dW if you do a separation of variables equals KT. And that is going to do a little bit of work to get you there. But what it has in that whole story is after 10 minutes, there was 850 widgets. So what I know is after 10 minutes, so it's 10, e to the k times 10, there was a total of 850 widgets. It says 5 minutes later, which would be 15, it had grown to 1,200 widgets. So what I would personally do is I'm just going to divide down. And if I divide it down, I'll have 1,200 divided by 850, which is a nice little fraction, 24/17. So I've got 24/17 equals e to the k times 5. Because remember, when you divide, you subtract things that have the same exponents, and notice the c's cancel. And now I could figure out what that growth rate is. And now it looks like I'm kind of going out of order because I am. So natural log of 24/17 would be 5k. So let's see what we have. The natural log of that divided by 5, I'm going to store that as alpha k because that's my growth rate. So my growth rate is 0.06896. In other words, around 7% growth rate continuously. Now, by doing that, there's a couple of things that I could do. And I'm kind of growing all over the place, but I know that I have this little equation that said I had 1,200 widgets at exactly k times 15. Well, this is really just a pretty simple number. So if I multiply that by 15 and I take e and I raise it to that power, all I have to do is take 1,200 and divide by this value that I just got. So let's see, 1,200 divided by that value. It looks like my initial condition C is 426.476. So there were that many widgets starting my story, okay? And then the last thing we have to do is what is the rate of change of the population at 10 minutes? Well, the interesting thing is it says the rate of change, see, keep in mind dW dt is equal to kW. Well, I know that at 10 minutes, I had exactly 850 widgets. And the growth rate I already had over here as 0.06896. Sorry, I didn't write that very well. So if I took 850 and I multiplied that by k, 850 times alpha k, the growth rate should have been at 10 minutes. The growth rate is 58.622. But remember, the more widgets we have, the faster the widgets grow. And that's kind of the way those problems go. A lot of times people think they're going to go back and actually find how many widgets, but it didn't ask for that. It asked for the rate of change, like how fast are they growing? And so that's problems 11 through 12. I'll be back on another video to finish 13 through 15. I'll see you later.